Click for IB Biology. Here we're looking at the movement of water in animal cells. We're looking at osmosis with respect to animal cells. We'll be looking at the different types of external solution that they might find themselves in and how unicellular and multicellular organisms might go about managing their water content. There's a blank PDF of this presentation down in the description, where you'll also find a link to 10 questions to challenge your understanding of this part of the course, and the answers are provided so that you can check out your progress. So we have discussed solvents and solvation and the effect that solubility has on water molecules. We're going to develop that idea here. So we start with the idea of a less concentrated solution, which is illustrated in my diagram here by only just one or two solute molecules here. So these would be soluble molecules such as sodium ions or chloride ions, or indeed both. And then we have a more concentrated solution, which is on the right hand side here, and you can see there are way more solute molecules on the right hand side here. So you'll remember that what happens is that where we have a solute particle, the water molecules become hydrogen bonded to it, and the consequence of this hydrogen bonding is that the kinetic energy of the water molecules becomes reduced. And so solute particles reduce the kinetic energy of water molecules. But also, the more concentrated we have, then the less total kinetic energy that there will be. And so the water molecules are free to move in both directions. But because the water molecules on this side here, have more kinetic energy, then most water molecule movement is from the less concentrated side to the more concentrated side. And so here we have an early definition of osmosis, the movement of water from a less concentrated solution to a more concentrated solution through a semi-permeable membrane. Now we're going to phrase that as being a low solute concentration. So water moves in osmosis. Water moves from a low solute concentration to the higher solute concentration. That's the movement of water through the membrane. But try to remember that the reason why it has that pattern is because on this side we have high kinetic energy of water molecules, and on this side we have, relatively speaking, lower total kinetic energy of water molecules. Taking that idea forward, let's introduce you to three phrases: hypotonic, isotonic, and hypertonic. Now these words refer to the external solution. Now I've copied out the rule for osmosis here. So this is our osmosis rule, so we're going to apply that now. In a hypotonic solution, the external solution around the cell has lower solute concentration. So in this one we have low solute concentration here, and we have a higher solute concentration here. So let's go to our prediction. So the water will move from the low solute concentration to the higher solute concentration. So it's going to go into the cell like this. Now the consequence of water going into an animal cell is that the volume of the cell will increase. And because there are no restrictions on the expansion of the cell, what is likely to happen is that the cell will expand, will reach its limits of its membrane elasticity, and it will burst, a process called lysis. So in a dilute solution of low solute concentration, the water molecules will move into the cell will swell and burst. if we have, let's go to the opposite extremes, which is a hypertonic solution. So this would mean that the external environment has a higher solute concentration. So the words hypo, iso, and hyper refer to the fluid round about the cell. So the external environment has a higher solute. So we have a high solute concentration here, relatively speaking, a low solute concentration here, and our prediction here suggests that the water will leave. And the consequence of that will be a volume reduction for the cytoplasm, which will then cause the cell to shrink. And the word often used to describe that is crenated. It becomes shriveled up and crinkled. So neither of these two solutions sound particularly good for an animal cell. So let's look at isotonic. Now iso means equal. And so the concentration of the solute in the external solution is equal to that of the cytoplasm. So the amount of water going in is equal to the amount of water going out. And so the volume of the cell remains constant. And this is an ideal condition for an animal cell. And so animal cells will pursue ways of controlling their situation so that everything remains isotonic. If we take a look at freshwater organisms such as the unicellular protoctists, living in fresh water, the situation is that the surrounding water will have a low solute concentration, and the cytoplasm will of course be the high solute concentration, and therefore the water is going to go into the cell. It should cause it to volume to increase, to expand, and it should burst, but they don't. And the reason for this is because they have a special structure called a contractile vacuole. So let me try and explain this. So here we have the contractile vacuole, this vesicle-shaped structure here. And with water coming into the cell's response is to pump potassium ions into this vacuole. Now that makes the vacuole concentrated. And the chloride ions and the potassium ions are in the vacuole. The water will then go into the vacuole by osmosis again. It's an internal movement shown here. So the water is going to fill up the vacuole. The vacuole will increase. Its volume will increase. It will get larger. And then it migrates towards the cell membrane. And with the secretion of calcium ions internally, this causes the vesicle to fuse with the cell membrane, and the water is excluded from the cell. So the incoming water to the protoctistin cell is controlled by the contractile vacuole by creating these vesicles that draw the extra water from the cytoplasm, and then the vesicle dumps that water to the external environment. So that's how a unicellular protoctistin cell deals with that. Our cells shown here are bathed in tissue fluid, and that tissue fluid is derived from blood. The tissue fluid around the cell circulates from the blood around the cells, and then it's actually drawn back into the blood like this. Extra fluid is drained into the lymphatic system. Now, therefore, the concentration of tissue fluid around our cells to be isotonic, it's necessary to control the composition of blood. So we have to have the blood plasma needs to be isotonic to the tissue fluid. And in our cells and in many of the animals, this is performed and achieved through the function of the kidney, which will be the subject of detailed study later in the course. Links to the next video are now showing to the channel and to the next playlist.